broadcasting from Miami, Florida. You can see the palm trees in the background there. I'm doing that to make our northern neighbors jealous. I have the sweater now because the temperature plunged to 65 degrees. So everyone has gloves and sweaters. Tonight, we're going to be talking about a title in nanomedicine, a title that Kristian gave me, but I couldn't believe it. I thought he was pulling a joke on me. Quantum dot technology for multiplexing applications. And I was going to say to him, geez, what a coincidence. I was just discussing that with my wife this morning. But I'm sure it's going to be a good topic that will be revealing in our quest to learn what the heck nanotechnology is and nanomedicine is and why it's useful and why it's good kind of to know what's going on in healthcare today. So, Kristian, just one quick thing, Kristian. Now, if you're watching, there's a tweet board next to the video screen. You're welcome to tweet questions or comments, and I'll be glad to collect them and address them to Kristian at the appropriate time. So, take it away, Kristian.
Okay, great. Thank you, John. This is actually our third video, our third time we're hosting this show, and certainly more to come. So, I think, one of the things that we wanted to kind of spring upon the audience is that we're starting to build a very nice set of logical, coherent topics. So in the first hangout, we had a really good chance of introducing what nanomedicine is in the broad scheme, talked about the broad implications, both government and non-government, and certainly looking at science, research, and we had a very interesting and engaging discussion. Then we kind of switched gears into looking at specific pharmaceutical applications for different nanomaterials, both mainly gold and quantum dot. And then today I'm going to look at one very specific diagnostic applications. What me and John hopefully are going to be able to accomplish in the coming weeks and months that the show is going to be going is to really start getting in different guest panels, scientists, industry leaders that are going to come with us, going to start explaining their technology. But really, one of the things that I want to segue and really emphasize is today is going to be the other core, I think, lecture on the diagnostic part of nanomaterials, which is then going to segue into very interesting topics in the coming weeks. I think what me and John are looking to start is, if we have certain guests, we'll certainly talk about their research, but getting into more broad-based topics like use of nanomaterials as anti-aging properties, use of nanomaterials in skin cosmetic applications, things that I think could have a lot of practical importance for people and understanding how this technology is interfacing with their day-to-day life, and certainly getting an appreciation for where the science is giving a very tangible effect. So, we have a lot of exciting things coming up. So today I'm going to be talking about what sounds like a very esoteric topic, quantum dots. As esoteric as they are, they're going to be certainly a very, very up-and-coming science. And as a material, they are really, really interesting. And I'll go into depth into how they play a key role in diagnostic applications. And certainly, as I stated, hopefully in the coming weeks with just guests and more interesting, more germane day-to-day topics, this is really going to help you at least put the diagnostic applications in perspective. Okay, so quantum dots actually, interestingly, was first discovered, certainly as in a byproduct of some stuff that IBM was doing with supercomputers and looking at different properties of quantum dots being conductors. The interesting part about quantum dots are that they are actually unique nanomaterials that are composed of the 2 and 4 elements in the periodic table, and typically they come in both spherical and non-spherical shapes. So again, I love to draw stuff on this graph pad, and I think it's a very interesting tool for us to be able to discuss this stuff. So let me show you what a typical quantum dot looks like. So this is a simple spherical quantum dot. And I think I had mentioned before, the basic premise of quantum dots is that when ultraviolet light strikes the internal core of the dot, it emits a composite wavelength of light that is able to be detected by different photoluminescence spectroscopy, and sometimes it can be as sophisticated as using a flow cytometry. But the basic premise is, if you can see here, these quantum dots are excited by an ultraviolet light, and then they emit their own wavelength of light, which then are picked up by different spectroscopy and equipment. Now, the interesting part about this is that if you can now change the diameter of these quantum dots, they can emit light at very different wavelengths, anywhere from 300 to 400 nanometers to the near IR range. And these quantum dots, the beauty of it is a single excitation light source allows these quantum dots to start emitting in very different wavelengths. So what happens? What's the advantage of, how does this play into a very specific diagnostic application? Well, the key idea here is, now I'll give a very good example. Let's say we wanted to describe John. I see John in front of me. John has glasses. John is wearing a blue sweater. John is wearing headphones, and John is having white stripes on his shirt. The current area of technology is that each of those, let's say, each of those characteristics that we described about John could be represented by a color. So let's say the color red codes for John's headphones, the color blue codes for blue sweater codes for John's blue sweater, the color green codes for John's glasses. The interesting part about using quantum dots as a diagnostic tool is that if you start to look at all of these characteristics in what we call a flow cytometry application, and you look at these three colors, what you would get is that anytime you take more than three colors, you get this effect where the colors start to bleed into one. So why does this happen? Well, because the current state of the industry is biological dyes function to label these specific characteristics. So how does this, let's translate that. So in the case of when we're describing John, that's a very specific analogy to how this stuff would be used in cellular work. If, let's say, scientists today wanted to describe different cells, they wanted to call something a cancer cell versus a non-cancer cell, each of the biological dye would be one specific characteristic for something that describes that cell that makes it different than any other cell. The problem comes is that eventually, because biological dyes have such a broad-based absorption and emission peaks, the colors can eventually, because the naked eye itself can only decipher 6 to 7 colors, eventually the colors will start to bleed together. What ends up happening? What ends up happening is, the obvious conclusion is, you set a limitation to the number of parameters that you can actually detect. So going back to my original analogy, if we're using biological dyes, which is where the current state of the field is, and you're trying to describe something, again, these are not absolute numbers. These are just purely for why quantum dots are serving to be such an interesting phenomenon in the field, is there's a limitation to how many characteristics you can describe using the current dyes. So going back to the analogy I said, if I were using biological dyes, maybe my output reader can only pick up John's eyeglasses, his blue sweater, and his headphones. Now, the advantage of using quantum dots is that with the same excitation source, whereby you originally were able to only pick up 3 peaks, the quantum dots now are generated in such a way that you could now pick up 10, 12, 14, 16 peaks in the same wavelength. So it's almost, you're going from 3 peaks to this many peaks across in the spectrum of light. So why is that advantageous? The advantage to that is now I can describe John, whereby because I have so many more individual peaks correlating to a specific characteristic, instead of describing John as just the guy who wears a sweater, a headphone, a blue sweater, a headphone, and glasses, now I can describe John as John has a blue sweater, he's got a headphone, he's got glasses, he's got blue eyes, and he's got palm trees in the back of his house. So you see where this could be a huge, really momentous, game-changing technology in the diagnostic field. Why? Because 95% to 100% of tests that you get in the doctor's office always talk about sensitivity. You get your blood work, you get your basic chemistry panels, you get your blood pressure measurements. All of them come with this idea of sensitivity, which is this concept is how good a test is at ruling out something. So the point that I'm trying to make is, if I was using a test to make or not make a diagnosis, and let's say my test was to identify John, I think that a physician or anybody who's placing a smart bet would say, yes, the more describing characteristics you have for John, naturally the likelihood that I'm going to get John right is going to be better than if you only told me 3 characteristics. And that is the basic principle behind why quantum dot technology is really pushing the frontier for diagnostic applications. It's allowing people to create this, and the word itself, which I had started at the title, multiplexing, multi-analyte plexing, which is the idea of being able to measure multi-analytes all at the same time. So I'll tell you one very, very important application: pregnancy tests. A lot of people don't realize that a lot of pregnancy tests are based on a nanoparticle platform. They use gold nanoparticles in a lateral flow assay format. And that's unbelievable. You get these things. There are some pregnancy tests that are coming out with this type of platform. Now imagine something even more elegant. Imagine now a pregnancy test has just a simple binary answer, yes or no. Now imagine something, for example, such as, hey, does this person have a certain type of cancer? Or does this person have any predisposition to certain types of cancer? Imagine being able to take somebody's blood, looking at a host of different biomarkers, which is a very big buzzword now at NIH, National Institute of Health, where a lot of research is getting funded. Can we discover biomarkers for specific diseases? Is there certain proteins or certain things that are being upregulated that can be detected from a patient's blood or urine sample? And that would give physicians the ability to just say, okay, this is a biomarker for cancer. He's got 15 of the 20 parameters that can be identified because we're using this technology. Therefore, the probability that in the long-term outcome this patient would or would not have cancer is Y, number Y. So this is a very interesting and very specific application for why quantum dots are really pushing the forum for diagnostic applications. Now, the next question, and I think the elegancy of this material, is quantum dots are unique in another factor, which is it's not just important that you're able to carry out these multiplexing applications. The second aspect of being able to deal with quantum dots is longevity, which is for example, how do I know that if I purchase these custom-made quantum dot nanomaterials and use them in these nanomedicine applications that are having very far-reaching implications in my day-to-day decision-making, especially from a medical standpoint, how do I know these dyes aren't actually bleaching? How do I know that there's no actual loss of efficiency in these quantum dot materials? So, in fact, one of the other advantages of quantum dots is they don't photobleach. So natural light doesn't actually force these materials to bleach out. And subsequently, another very interesting property is that because they don't photobleach, sometimes these quantum dots themselves are shelled. Because the core itself is the most unstable part of these quantum dots, they're typically double layered, and the double layering itself is what lends itself to long-term shelf life and stability. So these quantum dots, I mean, they stick around for a while. So for applications that are ex vivo, which means that you're not putting it in a patient's body. Remember last week I described a very specific application of quantum dots as a therapeutic application. Now I'm talking about ex vivo applications, which is primarily diagnostic. These nanomaterials can be very, very elegant in terms of having long shelf lives, relatively no photobleaching, and can really do multi-analyte parameter detection and diagnosis, which lends itself to being an incredible tool when you're doing multiplexing applications.
One quick question,
Sure.
Kristian. Now, you said biomarkers are markers of probability of certain types of cancers. So it's really not 100% diagnosis, or is that just one particular case you're talking about?
Very good question, John. So the key part of understanding biomarkers is that certain markers are going to have a better sensitive or better predictive value for how likely, obviously, for example, there are going to be certain markers that are much more or higher of a sensitive value for certain types of cancers than others are. Okay. So, I'm trying to think of a good example for a very definitive marker for something like prostate cancer or bladder cancer. And let me think of a good one that I think is
ovarian? No.
Ovarian cancer. I'm trying to think of something that has a near perfect sensitivity, which I think it might be difficult to do. But you're definitely going to have specific markers that are correlative to certain types of cancers. That's a given, and right. That's where a lot of these blood-based tests are based on. Okay. They look at what's the likelihood that somebody with upregulation of marker X is going to have cancer Y, and so yes, not every biomarker is going to provide you 100% sensitivity. And that's probably unrealistic because so many disease processes are going to be multifunctional. But nonetheless, there's a pretty good correlation to certain markers being more correlative to certain types of cancers than others.
You think we're headed towards 100% predictability, or
but
never will reach that?
So that's exactly that's the key part of this discussion, right? So when you're asking about predictability, it goes right back to why newer technology is going to change that. Okay. So if, let's say, it goes to the same example, if I was predicting factors that for why a person could have a high risk for colon cancer, you could say diet, you could say age, you could say family history, you could say certain tumor genes are being upregulated. There's so many prototypical factors that are affecting your outcome for yes or no decision that you may or may not get colon cancer. Okay. Now, if you go more specific to this example, let's say you were to measure that in the blood, and only 3 out of the 5 parameters you could actually measure because your device or your probes themselves had a functional limitation, then the predictive value is going to be a lot less than if you were to measure 7 of those parameters. So yes, the end objective is to say concretely, hey, I'm 100% sure that you're going to get disease X or disease Y, but that's really a matter of being able to actually get that many of those, all those parameters detected in a single forum, and that's kind of where the technology is going.
Great, thank you.
So, so this is, I think this is kind of what I wanted to talk about today, which was really looking at quantum dots as a diagnostic application. I guess we could, let me see if I can try to show some images of quantum dots in the diagnostic space. Let's try to. Okay, let's yeah. So this kind of a nice starting image, actually. Can you see these, John?
Yes, I can.
So this is actually from a some of our actual quantum dot technology. In I trying to show just an image of how these actual materials look in real time. And you can see this is actually some different formulations of quantum dots that are just kind of giving you an effect that the far left-hand side are the quantum dots that are in exposure. So all of these quantum dots are made of different wavelengths, different materials, different testing. So the far left-hand side is what you're seeing of quantum dots that are excited by UV light.
Mm-hmm.
And what I want to show you is a very interesting image. One second. Okay. All right, let me show you this image.
Okay, you're back to the screen, your screen.
Okay. Just give me 1 second. I'm just pulling it up right now.
Okay.
Okay. I'm surprised why it's not pulling up. Do you see the quantum dot image, John?
Not yet.
Oh, not sure why it's.
Okay, let me just go ahead. Let me just take this time to tell about the guests we may have coming. You just
Sure.
work on that. We may have. We've been in contact with a couple of guests, which I think will be quite interesting. Someone that's interested in nanomedicine. Paul Weiss, from a nanosystem scientist at UCLA, the head of the department, and I was very surprised to hear that he was willing to come and join us one of these coming weeks, hopefully. Olivier Fontaine, the editor of Nanomedicine in France. It's going to be hard to kind of arrange that. He's going to have to stay up late, 3 o'clock, if we're going to make this 9 o'clock time. Lejos Ballot, hope I pronounced his name correctly. He's editor-in-chief of Nanomedicine magazine in Boston. And Aidan Jacob at UCSF, interventional oncologist and also a neuroscientist. So these are all people that expressed an interest in joining Kristian in the coming weeks.
Sure.
Any luck, Kristian?
Yeah, I'm almost there, John. Just give me 1 second.
Okay.
Trying to. Seeing if I can get any of these images, but make best effort here. All right. I mean, I think what I think it'll suffice. I mean, I think the example that we had shown
Okay.
of the actual, this is a good example. It's a very nice example. So let's see if we can pull this one up. Okay. Let's see. So for example, I don't know why my screen share is not working at this point. But I mean, what I'll do is we can certainly next week when we get a chance, I can show you some of these images that we were collecting.
Okay.
But so I guess to summarize this discussion, so we had basically concluded that quantum dots were going to give us this ability to multiplex. So as we the plan going forward, and I think we've segued into several key topics. So we spoke a little bit about nanomedicine now. We've covered the therapeutic applications, and now we've discussed a very specific diagnostic application and how these materials work. So as John had mentioned, we have a very exciting set of guest lists, and as they start talking about their research, I think what we're going to do is the last 15 to 20 minutes, me and John will try to summarize some of their research as we also start speaking to them and engaging them. But what I'm going to do my best to do is using the principles that we've discussed about how therapeutics work and diagnostics work, we can certainly segue into explaining how those principles are interfaced into the researchers and industry thought leaders that are going to be coming on the show describing their work. So that was kind of the one thing. I did want to include this one part, which I think is really important, which is really explaining that, remember, the quantum dots in themselves are not what are the actual therapeutic materials. Or the diagnostic materials. They're just the probes themselves. How the probes actually detect an antigen or a material is through an antibody. Antibodies are the ones that actually bind to their target, and the quantum dots serve as the optical fluorescent probe. So whether you're looking at applications like Western blots, PCR, or you're looking at applications like an ELISA or sandwich ELISA, you're going to hear a lot of these very specific applications, but the principle is the same. The quantum dot serves as the optical probe bound to an antibody, and then the quantum dot antibody conjugate or complex or nanoplex binds to a very specific target. And in a case where you're looking at therapeutic, that target may be a specific cell in vivo. So the quantum dot bound to a drug goes in vivo. In terms of diagnostic applications, we're looking at that target being something like a specific biomarker that you're trying to detect. Does that make sense?
Yes.
Okay, great. So do you want to, I think we were going to run a shorter segment today, but do you want to go through some key interesting articles that you'd come up with? And we can
Sure. That's one thing I was going to actually surprise you with, but I guess you're not surprised. Oh, I'm just going to go over. I'm just going to show you. Let me get my screen back to me, or actually to the screen share here. Can you see that screen share of the articles?
Yeah, I do. It was there for a second, John.
Okay. Is it flickering or is it constant? Because I may be having a problem too with screen share.
Yeah, it came off and on.
Okay. Well, I think we had to scratch it last week too. This is a great program, but it does have some. It's not perfect, and it does have some bugs. But eventually, we'll try to get it to a point where Kristian and I will maybe at the end of the discussion just go over a few of the articles from the past week in nanomedicine, and just maybe make some comments on each one, or maybe whoever's on the panel can comment on these new discoveries, because it's a field as Kristen knows, it's changing very quickly. Things are happening constantly on a daily basis, and that's originally why we thought of doing this weekly, so that the healthcare community out there can kind of keep a handle on what's going on in the nanotechnology community. And there are certainly lots of things. And I don't know, how do you manage to keep up with things, Kristian, in your anesthesiology residency?
Yeah, and it's you got to be passionate about what you do. I think that says. But you know, I always say I'm fortunate because I was fortunate to be trained in both the physician side of things and the scientist side of things, and the convergence really lends to some very exciting concepts, and it's a very fun place to be. It's very challenging because you become a master of multiple fields in some ways, and it's lends itself to its own difficulties. But you know, I think we could have you could go a very in-depth discussion about the original reasons the MD-PhD program came about, originally from NIH in the 50s, which was to really create physician scientists. Mm-hmm. And so it's kind of it's a fun place to be because you see all this technology that could have so many practical applications for patients, and you can't appreciate that unless you're actually a physician who's able to interact with patients every day and who's really creating the right problems to study. Sometimes research without a clear end goal can feel like just an abyss that you're lost in, but when you're studying the right problems, it can have more value, and time spent is certainly of tremendous gain.
Well, that's why I really think that someday internet medicine will be a specialty, because I think to get the maximum value out of a physician, certainly ones that, as you probably know, ones that are really smart with computers, to use them, they have, like you say, the combination, scientist medicine combination, where they have the medicine internet knowledge. They can spot opportunities where, well, wait a minute, I can do this with the program, or I can do that, or I can use this internet application here. Whereas if they were strict medicine, they wouldn't realize where the internet would come in, or if there's strict internet, they wouldn't realize where medicine came in to relevance.
Yeah, and you're right, John. This is a different age. This is a digitalization age. Everything, everything from literally internet is the new modicum of knowledge transfer. Let it be from entertainment to any industry. So why not? Is medicine immune to that? No, it isn't. In fact, the more educated you are about information that's going on the internet, you're going to be a better informed doctor. Because patients certainly are not. Their internet becomes their primary source of information for even the stuff that they're reading every day.
Well, I'm kind of excited. I'm looking forward to the integration of the present internet generation, kids that grew up on the internet that are going through medical school now, and that are being unleashed into the practice of medicine. I'm very interested to find out that I think the increased efficiency and the increased application of the internet in medical areas. Well. Okay, Kristian, I think we kind of wrapped it up for tonight. So,
do you want to? I mean, I think unfortunately, we can't go through the articles, but so I think what I'd like to leave the audience with, John, and I think we've come to a very nice. So the way we want to structure this, I think going forward the show, what me and John were discussing is, certainly me and John will give an introduction. We'll start to present a little bit of the bio data of the different guests that are going to be coming on in the coming weeks, and hopefully we're going to start to create a theme for that night. If a certain guest is going to be able to present research in that forum, that'll be interesting, but certainly I think where I'd like to see kind of us have an impact is talk about the relevant topics of where nanomedicine is affecting things like, as I mentioned, aging, cosmetics, cancer, cardiology. I mean, some of the big topics that, literally when you go to the doctor's office, how can you see this technology start to play a role if it hasn't already? So certainly we're going to start picking topics where you're actually seeing this stuff in everyday practice of your or care of your health, and we'll start to discuss those things. So we'll certainly have a guest that will share his insight, but if not, we'll certainly, me and John will go through some of those topics with you, and we hope that whoever is listening or whoever is hopefully tweeting that, you know, we can certainly make this not just for the nanomedicine community, but for the community at large. So I think John, you would agree, right? I mean, I think we have a very exciting set of things coming up.
Oh yes, yeah, I'm looking forward to meeting some of these nationally famous guests. They're really curious. Well, first of all, I'm very glad that you took taken control of this night, and I'm very happy to hear from these very influential people in the nanomedicine world that seem kind of curious about the platform of Google Hangout, and LinkedIn, the social media, has allowed us to approach these gentlemen and ladies very easily. I'm very impressed with LinkedIn and other social media as far as reaching out. At any rate, we've kind of wrapping up. Okay, Kristian, I appreciate you taking time away from your busy anesthesiology residency. You were a little late because you had to even run to the hospital.
Right.
Thank you for taking time, and I look forward to seeing you next week.
Excellent. Thanks, John.
Good night. Okay.